So this is Solar Max, part 5 of the Exploring the Solar System series. So we know that if we're interested in studying the sun, this is the standard safety warning. The only time when it's safe to look at the sun, of course, is during a total eclipse when we can get a beautiful view of the solar corona. And I'm sure you know, but I'll tell you anyway, you should not attempt to look at the sun unless you either have the relevant eclipse glasses if you wanted to see a partial solar eclipse, or the relevant optical equipment if you wanted to study the sun during the day. And of course, keeping your eyes safe is important for everybody. And by everybody, I mean young and old, and regardless of which species you are, everybody has to protect their eyes. And some dogs can do it with a certain amount of style, and others not quite so much, perhaps, but okay. Right, so a reminder about our sun. If we plot all stars on a so-called Hertzsprung-Russell diagram with luminosity on the vertical scale and surface temperature on the horizontal scale, for historical reasons, colder on the right, hotter on the left, then we find our sun there with a luminosity of 1 times the luminosity of the sun, that's just a convenient unit to use, and a surface temperature of a little bit shy of 6,000 Kelvin or so. That's just a reminder of where we fit in the grand scheme of things. In many respects, our sun is unremarkable. It's not the most massive, it's not the least massive, it's not the most luminous, it's not the least luminous. It's relatively average star when you think about the entire contents of the Milky Way galaxy. A reminder of what's going on inside, as far as we know, because we can't look inside directly. We have the core where nuclear reactions are occurring, and then there's a zone where that energy is transferred out to the outer regions, where there's a whole sort of convection zone as the heat starts to make all of the plasma of the sun start to churn around. And finally, the photosphere is the visible surface that we see. So arguably, we have to infer a lot from what we see from the sun on the very surface of the sun and deduce what's going on under the surface. Occasionally, we get some parts of the plasma. We don't have neutral atoms in the sun. It's so hot that the atoms are split into their positively charged nucleus and negatively charged electrons. Collectively, this is simply called a plasma. So we have a hydrogen plasma, and sometimes this plasma produces prominences. Some of those prominences rise up and then fall back onto the surface of the sun. Every once in a while, a prominence can be released and a whole load of material is released from the surface of the sun and effectively obtains escape velocity and heads off throughout the solar system. What's going on in the core is thermonuclear fusion, whereby on the left we have 4 nuclei of hydrogen, or 4 protons if you prefer, and ultimately they get fused into 1 nucleus of helium, which is 2 protons and 2 neutrons. And the process by which you take hydrogen and fuse it into helium releases energy. The mechanism, the process, I'm not going to go through the details because there's more than one step involved. It actually involves quite a few steps to go from 4 protons to 1 helium nucleus. But the bottom line is that every second of the sun's existence, it is converting 620 million tons of hydrogen into 616 million tons of helium. And of course, there's a difference there. There's a 4 million ton difference. So every second, 4 million tons of stuff winks out of existence and produces energy, which ultimately keeps the rest of the solar system lit with sunlight and hopefully warm as well. So we don't worry ourselves about the mechanism of the details. And although it's losing 4 million tons of mass every second, given that the sun is fairly large, that will continue for something like 10 billion years quite happily. Also notice that actually the sun doesn't get a lot smaller. Over that 10 billion years, it only loses about 0.5% of its mass. So in other words, the mass of the sun at the end of its life is going to be very similar to the mass of the sun at the beginning of its life, simply because that 4 is a relatively small fraction of the 6 million tons that is converted from hydrogen into helium. All stars are a question of balance. If we think about it, gravity is always pulling in, and the radiation that we've just been describing, the nuclear reactions at the core producing radiation, are effectively pushing out. And as long as those two are in balance, then everything is hunky-dory and we have a star that's in balance. That's basically where we are now because the sun is middle-aged, and this will continue for another 5 billion years or so. One thing to bear in mind, it's not directly relevant to what we're talking about, but it's often misrepresented, and that is that the length of time it takes for the radiation, the energy in the core of the sun to actually reach the surface is enormous. It might only take 8 minutes once it's reached the surface to arrive at Earth, but it can take hundreds of thousands of years for the energy from the core to actually make its way to the surface, simply because the sun is so dense. What's going on inside the sun? I said we can't see it. We can infer something about what's going on inside the sun. And one thing that's been done relatively recently in past decades or so is to look at so-called helioseismology. Just like an Earth scientist would use earthquakes, waves of sound traveling through the Earth's crust to try and work out what the Earth's crust and the Earth's mantle and the Earth's core is made of, then something similar happens in the sun. Sound waves can allow us to get an idea of what's going on inside the sun itself. Now, you can see here what we've got is not necessarily the temperature and density directly. This is simply an indication of how fast things are moving inside the sun. It would appear that the equator, so this, remember, is a slice through the sun, so there's the center of the sun. Here's the equator, the horizontal. We can see that the outer part of the sun here is rotating quite quickly. In other words, the sun is spinning once in 25 days, but unlike the Earth, it's different at different latitudes. If you go to higher latitudes or more southerly latitudes, you can see the length of time it takes the sun to rotate is significantly more than 25 days. It can be many, many days slower. And to the best of our knowledge, it also changes as we go deeper and deeper into the sun. We still don't really know what's going on in that white area. The helioseismology can only give us a limited amount of data about how the sun is moving internally. Of course, what we see of the sun is the photosphere. When we look at the sun, regardless of whether we're looking at all wavelengths of light, usually called white light, or whether we look at particular wavelengths, like the wavelength corresponding to calcium or the wavelengths corresponding to hydrogen, we can get a little bit of different information about what's going on. Most of that is in the same sort of region of the surface of the sun. And that's how, historically, we've got most of our information about what the sun is doing. More recently, we have more technical ways of delving inside the sun, but for many hundreds of years, we relied on the fact that it's the surface of the sun that we need to examine or study. We know that parts of the sun occasionally get released. We occasionally have not only prominences, but coronal mass ejections, and these can be released, and some of them might come our way towards the Earth. And the Earth's magnetic field protects us from much of the radiation from the sun, but every once in a while some of that can get through, and then we get the beautiful aurora seen here from Iceland back in 2002, close to a solar max of a little while ago. So again, the entire sky lights up when you get an auroral display, and you get spectacular curtains of light. Perhaps you can recognize the Orion constellation just about peeking through. Some of the stars, the aurora can be so bright, sometimes you can't even see the stars through the aurora. And depending on exactly what time of night you catch them, you can get these beautiful curtains of light which shimmer almost like they're waving in the breeze, even though these curtains of light are perhaps 100,000 kilometers or so, 100 kilometers or so in height. So it is truly fantastic sight. But if we think about what we can learn not from looking at our atmosphere, but from directly observing the sun, which we will do safely, of course, one of the earliest bits of recorded history we've got about people observing the sun is back here in 1128. It's not clear whether or not this was an observation made on a foggy day, or whether it was made at sunset, or whether they had a pinhole camera of some kind, but the indication is that there was a very large sunspot on the surface of the sun. But if we move forward many centuries, we know that Galileo was one of the first to meticulously document sunspots. And here we can see over a period of many months, we see the sunspots moving across the face of the sun. Again, a rather important observation that indicated that these were genuine features of the sun, not simply something floating in our atmosphere that happened to get in the way between us and the sun, by noting that some sunspots came round more than once. Some people were more flamboyant as to how they interpreted sunspots, whether they are little campfires producing smoke. Again, it took obviously a few centuries for us to understand what the sun actually was, and hence what sunspots actually were, regions of the sun's surface that were a little bit lower temperature than anything else. But I find it remarkable that in 1873 people were able to observe sunspots with such remarkable accuracy that they could produce drawings like this. You realize that the technology available to them was limited to compared to what we have today, and yet they were capable of producing images and pencil drawings like this one. Absolutely stunning, especially when you compare it to the best we can do today and look at that for a detail on a sunspot. A sunspot is a region of the sun where heat from below is finding it more difficult to come through the surface, and hence the surface is a little cooler. It might look black. It isn't actually black. It is white hot, but it only looks black because it is dark. It is cooler than the rest of the surface. The surface on average is about 6,000 Kelvin, and the middle of a sunspot might be about 4,000 Kelvin. On its own, that would be glowing like an arc welding arc. It's only looking dark simply because 4,000 Kelvin is a little bit cooler than the rest of the surface. But look at the amount of detail that we can see in a sunspot there. And a reminder of the scale, there's a few thousand kilometers in the scale bar in the bottom left there. When we look in detail at the surface of the sun, it is by no means static. Remember, we're talking about a convective system, and therefore we see convection cells, like if we were watching water boil in a pan, for instance, being heated from below. These things, again, if we think of the size, there's the Earth to scale. So these things are the size of a continent or a small country. They are huge in terms of individual things that we can think about, but tiny in terms of the overall scale of the sun. Let's think about the activity of the sun. We can judge the activity of the sun not necessarily by counting how many prominences we have or how many times we get a coronal mass ejection sent out and thumping into Earth to give us an aurora. We can get an indication of the activity of the sun simply by counting how many sunspots there are. And we can see that if we do that, we can see that there are definite cycles where there are lots of sunspots, and then a few years later, very few, and then lots of sunspots, and then a few years later, very few. And by monitoring sunspot activity for the last few centuries, we've been able to determine that the sun has an 11-year cycle. Notice that before this particular point, 1750, the observations of sunspots were not particularly methodical. Therefore, we have some data, but it's not quite as reliable. But it does look like there was a period in between 1650 and 1700, there does appear to be a period called the Maunder minimum where the sunspots disappeared and didn't come back for quite a few years. And we still really don't understand what was going on there. The data appears to be reliable enough that that is real, but we're not too sure what actually was going on. Since then, or at least since 1750, we've got reliable data that tells us the activity of the sun comes and goes on an 11-year cycle. If we were to have a look back any further, we haven't got observations of sunspots, but if we imagine that that's our 400 years of sunspots condensed into that tiny bit there, we do have a proxy for solar activity. And the proxy is that we can use the amount of carbon-14 in the Earth's atmosphere as a proxy for how active was the sun. C14 is a radioactive isotope of carbon. It's used for carbon dating. It's made by cosmic rays, and the amount of cosmic rays that arrive on Earth depends on the activity of the sun, because that changes the magnetic field in our solar system and changes the amount of cosmic rays that arrive on Earth. So by correlating the two and working backwards, we can get an idea of what solar activity has looked like in past millennia. And yes, it has changed. It hasn't changed by a factor of 10 up or down. And whether or not that is in any way related to climate change, by looking at how things have changed, it doesn't appear to be correlated to the changes that we've seen. Changes on the global scale of the Earth's climate are more likely to be due to changes in the Earth's tilt or changes in the orbit of the Earth, or of course, man-made influence, but not how much activity there is on the surface of the sun. We can also go the other way and say, well, what's going on here? This particular graphic seems to end in, I can't remember which year, but in order to make sure this was as up to date as possible, I started plotting the sunspot numbers for the last few months. So there it is for the last few years. We might expect, based on what has happened in previous activity cycles, that the sunspot numbers, it was predicted, would go up, would maximize around 2025 and then start to come down again, and then the next solar minimum would be sometime in the early 2030s. And the black tells us what is actually happening, the actual number of sunspots that have been recorded over the past few years. As of a few months ago, I thought this was rising and looked like it would continue rising. But the last few months have shown this rather unusual dip. I don't, again, understand why it's dipped quite so dramatically. And it's difficult now to say, well, what's the next few months going to look like? Is it going to continue rising and then start to drop off? In other words, is the maximum of solar activity roughly where they predicted it was going to be, essentially here and now, towards the latter end of 2025? You could say that if that dip there is the start of a decline, maybe it's going to drop off faster. Maybe we have already effectively passed through solar maximum and are starting to move our way towards the minimum activity of this 11-year cycle. But because we are so high up there, because the activity is not only close to maximum, it's also higher than what was going to be predicted for solar maximum. That's why we've been getting such auroral activity, especially in the UK. As we were discussing earlier, you can't usually see the auroral activity. In other words, our eyes are not very sensitive to colors and faint light at night, simply because the way our eyes are constructed, but cameras can produce some of the glow that's seen there, the pinks and the greens. Nothing like as spectacular as the auroral curtains that you can see if you go to the Arctic or Antarctic to see the northern or southern lights, but it's nice to see that you can pick up some of the colors simply because the sun is so active these last few months. So what's actually going on with the magnetic field of the sun? This seems to be intimately linked to its activity. And working out what's happening in the magnetic field of the sun and working out what's going on inside the sun and inferring the magnetic field in there, again, this is really tricky. It has to be done by solving a lot of rather difficult physics equations and using simulations to try and tell us what's actually going on. But the bottom line is, when we think the sun is close to solar minimum, the magnetic field, indicated here by these colored lines in the north and the south, looks, well, not that different from what we would expect from, for instance, the magnetic field of the Earth, a so-called dipole field. If we had a large bar magnet in the middle of the Earth, it would produce these field lines. And that appears to be the sort of field lines we get from the sun when it's around solar minimum. And we can, of course, map out magnetic fields quite easily just using iron filings. Doesn't work so well for the sun, works fine for a little bar magnet sitting on a table. So we've got an understanding of a very simple magnetic field for when the sun is close to solar minimum. But if we compare that with what the magnetic field looks like at solar maximum, it's an absolute mess. It appears to be far from a simple dipole bar magnet type field. It's as if there's all sorts of other activity, and it's almost like it's got extra north poles and south poles popping up all over. And we think that's related to the activity, not least through the fact that when we look at it carefully and carefully study sunspots, we realize that the sunspots don't go through an 11-year cycle, they go through a 22-year cycle. In other words, the spots arise and then they disappear. But when they come back again 11 years later, the magnetic polarity of the sun, the north and the south pole, have flipped over. And then the spots come back and then they disappear, and then everything gets back to where it was 22 years ago. So the magnetic field appears to be absolutely central to understanding the activity of the sun. But why is it so complicated? Well, it's complicated for a number of reasons, not least the one that I hinted at earlier. With seismology, with helioseismology, we've determined that the sun at the equator rotates in about 25 days. But when you look at higher latitudes, the sun takes about 28 or 30 days to rotate. It's a fluid system. It's not like a solid object like the Earth or other planets. So what's going to happen if we have magnetic field lines? Let's say we start with very simple magnetic field lines threading through the sun. Now we allow the equator to spin at a different rate to the poles. What's going to happen to those magnetic field lines? The sun is a conductor. It's a plasma. It's got lots of positive and negative charge. Those field lines are going to get dragged around with the sun. So if different parts of the sun rotate at different speeds, it's going to twist and distort the magnetic field lines. And that is essentially why the field of the sun gets so distorted over time. That is, of course, just a little bit of a rotation. But remember, if it takes a month or so for the sun to rotate, then after a few years, things are going to get very, very tangled and very, very complicated. And this is a simplified version of what's going on inside the sun. Now, I know it's horrendously complex, so I can simplify this to 2 words. It's complicated. And I was told when I was a PhD student, don't attempt to understand these systems because it is way, way, way too complicated. It's called magnetohydrodynamics, MHD for short. It's how things move, the dynamics of when you're dealing with a hydrogen plasma in a magnetic field. And it is one of the most difficult things to deal with, not necessarily in terms of getting your head around, but just solving the equations that you might be able to set up for a large ball of plasma behaving like the sun. It is a horrendously complicated problem, and it needs supercomputers to run simulations to stand a chance of understanding what the magnetic field inside the sun is actually doing. The only way we can glean what's actually happening is not by looking inside the sun, but if we take one of those little cartoons, we can see that as the magnetic fields get more and more tangled, more and more wrapped up, you can almost imagine taking a rubber band and twisting it and twisting it and twisting it because of the rotation of the sun. Eventually that rubber band is going to produce bubbles and it's going to produce distortions, and sometimes those little bubbles can break out through the surface of the sun. And we can actually see that because if we actually image the surface of the sun, what do we see? We see signs of the plasma following magnetic field lines, which are these loops. And these loops are none other than the magnetic field line which is popped out from the surface of the sun because it's getting so tangled by being continually rotated and rotated and rotated. Eventually, these magnetic field lines snap and the whole thing resets. But basically, it is a very complex system, and that's one of the reasons we study surface images of the sun like this one to try and get an understanding of how these loops of magnetism are related to features on the surface. And we believe that basically these magnetic loops pop out of one sunspot and enter back into the sun through another sunspot. So sunspot activity is definitely related to changes of the magnetic field on the surface of the sun. What can amateurs do in terms of observing the sun? Well, one option is to take your telescope and put a filter, making very carefully checked that this particular filter is safe to use and is blocking 99.9% of the light, and then you can see the surface of the sun and see sunspots. Alternatively, project the sun onto a sheet of paper and then you will again see the sunspots themselves on the so-called photosphere. The alternative, if you can afford it, is a solar telescope. These are telescopes which are rather more expensive than standard nighttime telescopes because they have the ability to only let through the light from hydrogen or some other selected wavelength. So instead of letting through all light, they let through light of a very narrow range, and that allows you to see what's going on just above the photosphere. So you can see not only the sunspots, but lots of other structure around them. And at the edge of the sun, you can see prominences as well as filaments. Filaments are effectively just prominences seen from above rather than seen from the side, as we get at the edge of the sun there. So that particular telescope is one which has a 60mm lens on the front, not a particularly large telescope. 60 millimeters is not big by amateur standards, but it does allow you to get some wonderful images of the sun. These I took with some friends of mine, as you can see, more than a year ago now, back in September 2024. And it's amazing how much detail you can see on the sun with a solar telescope like this. If we blow up, for instance, this original image, blow up that region, you can see there's an enormous amount of detail surrounding a particular sunspot itself. These dark ribbons here are prominences as seen from above. If we were to look at them from the side, they would be arcing prominences coming up from the surface of the sun. Every once in a while, we do see prominences coming off the side. This was a particularly busy period, this May 2024. There were lots of prominences, all sorts of activity. If I blow up this region again, you can see that if you wanted to either watch or image, these things change hour by hour as this huge plume of hydrogen is thrown off the surface of the sun and perhaps either collapses down or is thrown off completely. If you remember the scale of the sun, the Earth would be approximately the size of that sunspot. So these prominences are absolutely huge compared to the size of the Earth. As well as amateurs doing things like that, of course, there are lots of professional telescopes around. There are professional solar telescopes throughout the world, including on the island of Tenerife. And at the top there is a solar scope. That's where we take our students. The universities of Liverpool take students out to Tenerife to do some nighttime observing, but during the day, if possible, we also show them what's going on these solar telescopes. So that's Mount Tidy in the background, and here's a telescope pointing at the sun, which you can never do unless you are using proper optical telescopes, and then the information is fed down the Gregor Tower to analysis instruments below. There are other things around the world. For instance, in Hawaii, there's the WU3A, apologies if that's not quite the right pronunciation, solar telescope, and there's a European solar telescope being built. I'm not sure it has a name. At the moment, it's being called the EST, the European Solar Telescope. They need a better name than that, but that's going to be built again on the Canary Islands in the near future. Solar Dynamic Observatory is the space telescope, which currently has a lot of telescopes, each looking at a different wavelength at the surface of the sun, and each wavelength gives you different information about what the sun is doing in terms of its dynamics, in terms of what elements are present and how they are moving. And perhaps you've heard also that we would like to get a close-up of the sun, and Parker Solar Probe is a probe that's been sent to get as close to the sun as possible without it melting, to get, again, more information about how energy is distributed from the surface of the sun out to the rest of the solar system. It's not just missions that are dedicated to solar observing. There are lots of spacecraft which are getting information about the sun, even, for instance, rovers on the surface of Mars, because although their job is to rove over Mars and look at Mars, well, they're also capable of measuring how much radiation is coming from the sun. And so spacecraft throughout the solar system, not necessarily pointing directly at the sun, not necessarily orbiting the Earth, they're all contributing to our knowledge of how space weather happens. In other words, how the sun dominates the effect of energy coming from the sun to the rest of the solar system. So if I've piqued your interest, there's a lot of very useful information on the NASA web pages about how the sun works, and all of these missions that I've been talking about and these space telescopes that will be coming online very shortly can be found at these web addresses, which are in the handouts if you want to take one away with you at the end of this afternoon. Thank you all very much.